Over the next two classes, we'll discuss chronic penny model. Chronic penny model as shown here. This deals with a particle in a periodic potential. We choose practically important issues of quantum physics from now on and consider a particle in a periodic potential. This is also called as chronic penny model, useful for understanding how electrons behave inside crystals. Our goal is to find the wave function and energy state for an electron in such a periodic crystal lattice, exemplified in a figure below in this figure. Here we see periodic atoms aligned at fixed positions along certain orientation, forming lattice. This is actually very important concept in engineering. You see dots here. Each dot indicates an atom. Okay. Atoms are aligned at fixed positions along certain orientation. So there are two different conditions here. Certain orientation, it means atoms are aligned along this direction. They align along certain direction. It is orientation. Orientation. And it has order, so we can call it orientation order. Okay, order. And then it is fixed at certain positions, and their distance is said to be always equal, like fixed value of d. So in this case, we can say that the lattice has position order. Okay, if we have two different orders in the lattice, then we call it crystal. Okay. So basically, crystal is the backbone of semiconductor materials and devices. So it is important concept. The periodic potential is due to the periodic arrangement of atoms in a crystal. To simplify the problem, let's consider our repeated rectangular potential shapes in 1D. Here it was 3 dimension. We will consider 1 dimension first, called chronic penny potential. If there are n atoms in the crystal, the total thickness L is equal to nd with a period d, and this d is also named as lattice constant. So let's discuss the periodic potential here. The potential field is a periodic function as sketched in figure 3.11a. At the location of each ion, we use the term ion now. The electrons are attracted by the ion and have the lowest potential because there is Coulomb attraction between the electron and the ion. So when you have electron, there might be many, but let's just consider single electron for now. Let's say we have electron here. The electron is originally detached from the atom. So the atom is now becomes the ion. Actually, positively charged ion it became. And the electron and ion should have Coulomb attraction, which is strongest at the center point of ionic position. That Coulomb attraction is now strongest at this position. So when electron is around this position, Coulomb attraction will be very strong and is moving around. It goes to here. The Coulomb attraction will be minimized, and it is strongest, minimized, becomes strongest, minimized. Yeah, Coulomb attraction maximized, minimized. It is repeated. So in this figure, y-axis is the Coulomb potential energy. X-axis is the position of the electron. The distance between the ion is A plus B. A plus B could be said to be D, and D is that something called lattice constant. This periodic potential shape is simplified like this because it is too hard to solve. So we rather use these structures. So it is called as multiple quantum wells. And here in this case, this one electron model under the rectangular periodic potential is called the Kronig-Penney model. So the potential is periodic. And previously we solved the finite potential problem with region 1, 2, and 3. Okay, now it is repeated. So now we need to consider that repeated potential concept. Otherwise, things are similar to what we have discussed before. Now we consider Schrödinger equation. So basically region 1, region 2, region 3, they have different potential shape. And region 1, region 3, let's presume that it has the same potential height, U0. Let's presume that in region 2, the minimum of the potential is said to be 0. Okay, because potential is important only in relative terms. Okay, the relative value in quantum and in the barrier is important. Okay, we don't care the absolute value here. So the potential is defined as shown here. 0 in region 2, where x is larger than 0, smaller than a. In region 1, it is u0, where x is larger than minus b, smaller than 0. And we see that potential is repeated. The period is a plus b, right? So this period is actually the lattice constant. Lattice constant, let's set it to be d. So yeah, potential is periodic if you add by lattice constant, then things are just the same. Okay, this d is the lattice constant. So the corresponding Schrödinger equation is shown here. Here we expect the electron probability to be the same in all unit cells of the crystal. So the range where we can discuss the potential shape is called as unit cell. So this scale a plus p is unit cell. Actually, this is the concept of three-dimensional description of crystal. So if you don't understand all those things, still it is okay. Okay, but at least the region describing crystals is called as unit cell. The crystal is formed on the basis of unit cells. Okay, we attach different unit cells, then it becomes crystal. Anyway, each cell, unit cell, is identical, and the most probable candidate for equal probability over space is plane waves. Surely our electron won't have plane wave functions. Okay, this is the case when we don't have any potential. This is the pre-particle case we previously studied. But it is periodic, okay, and each cell is identical in spread over space. So we might consider something is periodic and spread with equal probability in space. Yeah, this one has the equal probability in space, so we can consider this. Okay. And then we consider that psi cannot be plane wave since potential is not true anymore. So let's presume that wave function psi is e to the ikx multiplied by ukx. Okay. Here ukx is a periodic function with a period of a plus b or d. And this ukx is called as Bloch function. And actually, when the potential is periodic, we can set wave function like this. That is Bloch's theorem. Okay. So we can prove this, but we'll just accept for this class. For the proof, we can see some more detailed quantum mechanics classes, but in terms of application, actually we don't have enough time to prove, or it doesn't matter that much actually. We just accept and think about how to use it. Okay. That's the basic, what should I say, mindset of this class. So this is something called Bloch theorem or Bloch's theorem. You will repeatedly see this when you study the semiconductors or any crystal related studies. So we can easily see that psi x plus d, so it is shifted by d, then we put x plus d here instead of x, then e to the ikx, e to the ikd, then ukx plus d, and this is just the same with this one, ukx. So this is just the same with psi x. So we have just additional phase in the exponential function e to the ikd. Okay. Let's imitate the square quantum case as we did before. Then in region 2, where potential is 0, so this Schrödinger equation is now simple, just like free particle case. Then the solution is shown here. Here, as we did before, this minus h bar square over 2m, we divide both sides by this, then we will have psi double prime is equal to minus h bar square 2m e psi, and here this one we will set it to be large k square. Please note that we use large k here, we used small k here, and this small k is called as crystal wave vector or wave vector of the crystal, and it has also certain meaning for this. Once you study Bloch theorem, you'll get to know the details, but roughly speaking, this small k is the crystal wave vector, and it can be same as like this. So crystal size and m is the integer, so it could be 0, plus minus 1, plus minus 2, and so on. Okay, if you don't know that, still it's okay. You repeatedly study the meaning of this in your future. Okay, anyway, so the wave function in region 2 has this solution a to the I large kx plus b to the minus I large kx, and k is defined by square root 2me over h bar square, so that energy is equal to h bar square large k square over 2m in this region 2. In region 1, okay, this region, u is u0, okay, so in this case we move this onto the right hand side, and then we divide both sides by this one minus h bar square over 2m, and we solve the equation. Then you will have wave function like this. This is actually exactly the same procedure we did for the finite barrier problem previously. So in this case, c to the e large qx plus ed e to the minus large qx. Here q is defined by square root of 2m u0 minus e over h bar square. Previously, in the case of finite barrier problem with single quantum L, we sometimes ignore one of this, as you remember, because x goes to infinity. But here x doesn't go to infinity or minus infinity. It's finite range, so we should have both terms now. Okay, that's the difference. Okay, I'm pretty sure if you solve the finite barrier problem with single quantum L, you will get to know what I'm saying now. Okay, so we leave both C and D to be non-zero for now. Okay. And in region 3, psi x is defined like this from Bloch's theorem. Okay. Psi x should be the same with e to the I k d psi x minus d based on Bloch's theorem. So let's say x is now region 3, okay? Then this must be region 1, okay? So because it is now shifted, by d. So this one now replaced like this because we know psi 1x, right? Here instead of x, we put x minus d, right? So we have this in region 3. Okay, so we also have region 1, region 2, and region 3. We have 3 different wave functions. And now we consider boundary condition. So at x equals 0, psi 1 and psi 2 should be the same. X equals 0, then exponential functions all become 1. It goes to 1, goes to 1. So c plus d, this one just the same. X equals 0, then it goes 1, 1. So a plus b we have. So a plus b equals to c plus d. And then we take the first derivative. They should be continuous. Then we will get, take the first derivative, then ik minus ak minus ik multiplied, right? So I large K A, and then here minus sign we have, so this one we will have, and then now again x equals 0, right? The exponential functions will be 1. In region 2, we go through same procedure here. So we take the derivative. So q should be multiplied. Minus q should be multiplied. Then set x to be 1. So exponential function becomes 1. So we have this one, like this. We apply this process for the boundary of x equal to a. So again, psi 2 is equal to psi 3 at the interface. Psi 2 prime, psi 3 prime should be the same. Then we have this goes psi 2 is here. Let Let me erase a little bit. So psi 2 is here, psi 3 is here. So we apply the boundary condition. So x equal a, so x equal a, x equal a, then we have this one. Okay. Then x equal a, x equal a, right? Then we have this one. We take the derivative here. Yeah, then ik minus ik should be multiplied, and then x is replaced by a, then we have this one. Okay. Surely there is I, but in this case we should have I here. Right? There should be I. It is actually hidden by this blue panel, a navy panel on the left. Actually, there should be I here. So, on the case of right hand side, in the case of right hand side e to the ikd, we take the derivative, so q and minus q should be multiplied. Then we replace x by a, then we have this one. So from the boundary conditions, we have 4 different equations. Actually, we have at least 4 parameters to decide, and because there are 4 different equations, we'd better use matrix equation now. So they are formulated like this. Okay, 1/4 matrix here, A, B, C, D. So if you move the terms from right to left, move terms from right to left, and right hand side will be 0 matrix. Left hand side, they are arranged like this. So we have 4/4 matrix, right? Like this. So actually, you'll solve something more in terms of matrix equation from now on, and this will be the homework problem actually. Here, please note that A, B, C, D cannot be all equal to 0, because if they are all 0, then wave function should be 0. It means electron doesn't exist. So it is physically wrong. So if this is matrix M, and if the sometimes matrix is indicated like this, vector is indicated like this, so ignore this, but we have matrix. This M matrix exists. I mean, inverses exist, I'm sorry. Inverse is existing. Then A, B, C, D should be equal to 0. Okay, right? Which is wrong. So, inverse matrix should not exist. Therefore, inverse matrix should not exist. Therefore, the determinant of M must be 0. Right? Yeah, so this is actually from the linear algebra class. Okay. Then how can we calculate determinant? This is the mathematical representation of determinant. determinant. So can you calculate the determinant from this? And then you can simplify the determinant is equal to 0. That equation is actually simplified like this, 3.31. And this is actually homework number 3. I think we sometimes see these kinds of problems in engineering and also in science many times. So your softwares like MATLAB, Mathematica, they always use matrix formation. Well, you don't need to calculate yourself. I mean, it is often just calculated analytically by those softwares these days, but you should have your own intuitive picture of what is going on. So, try yourself to calculate the determinant of 4x4 matrix. But I'll let you know the basic idea here. Okay, so we know that the determinant of 2x2 matrix, for example, A, B, C, D, then we consider the determinant. We know it is A, D minus BC, right? This is what we learned from high school. And then in the case of 3x3 matrix, we have A1, B1, C1, A2, B2, C2, A3, I'm sorry, A3, B3, C3, yeah. And then take the determinant. In this case, yeah, we have simplification procedure. For example, if we choose first A1 here, then yeah, well, this one and this one should be ignored, and we consider the rest of the matrix, and then consider the determinant like this. Right? Okay. And then second row, we have A2. We put A2 and then minus sign. And yeah, same row, same column ignored. And we arrange the rest. P1, C1, P3, C3. And then A3, the rest is like this, same row, same column ignored, P1, C1, P2, C2. And then we calculate the determinant here, right? Yeah, just like that, we can do it for 4x4. Okay. Let's say now we have 4x4 matrix. So we have 4x4 matrix. Then now we need to expand this to A4 matrix. So we have A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3, D3, A4, B4, C4, D4. Then calculate the matrix. It will lead to like A1, and then there is 3 by 3 matrix. This row, this column, ignore, and we move this part here. Okay, right? And then for A2, we move this one and this one, and the rest move here. Okay, for A3, same row, same column ignored, and the rest we moved here. Then minus A4. Now you know the process. Yeah, same row, same column ignored, and the rest moved here. Then we calculate the 3 by 3 determinant. Right? We make it simple and simple all the way down to 2 by 2. Okay? So it is a little bit process with patience, but I think everybody can do that, right? If you go through that process and determinant is set to be 0, so you have this equation 3.31. Okay. All right. And we will consider simple case again when barrier thickness is thin. Barrier thickness actually from the periodic potential shape like this. We said the period is D, and then source minus B 0 A plus B plus B equal to D. Okay, so barrier width is B. So barrier thickness is in. So let's presume B is approaching 0, and height is large. Height U0 is approaching infinity, but still B multiplied by U0 is constant. Okay, then we want to simplify this equation. Okay, remove this, remove this. Okay, so this equation is simplified like this. Cosine KD on the left, and Q square minus K square over 2KQ, and sine KA, and sine hyperbolic QB now becomes QB, and cosine KA, then cosine hyperbolic QB is here. Okay, so actually it's almost 1 because here QB is very small. Since Q is defined like this, Q to 2m U0 minus E over H bar square is finite. Okay. Well, this is bound energy actually. If you have this potential shape, you have this energy. And this one is U0 minus E. Bound energy. This bound energy is here, and Q is depending on that, so it is finite. And B is becoming very small, so QB is very small. And QB is very small. You consider sine hyperbolic function in the expansion. So this is the sine hyperbolic function. When x is very small, sine hyperbolic function is same with x. Cosine hyperbolic, same with approximately 1. Okay. So then sine Ka QB plus cosine Ka 1, so ignore it. And then here we compare Q and K. This is Q and K is a function of energy. 2me. When you compare these two, because U0 is very large, at least Q is much larger than K, so we ignore this K compared to Q square. So Q square and another Q is here, so Q over 2K. Here actually Q square AB over 2 is said to be P. So let's see. There's another Q is here, right? So Q and Q should be multiplied, so Q square, and then P. We multiply A on both sides of numerator and denominator like this. So Q square AB over 2KA, and then Q square AB over 2 is actually said to be P. Okay, this one is said to be P. Okay, and you can go through this process, but let's make it simple like this. P over large Ka sine Ka plus cosine Ka now should be cosine Kd, right? So here small k is the lattice dependent property. Large K is dependent on electronic energy. Okay, dependent on electron energy. And small k is crystal momentum or crystal wave vector, we call it. So it is lattice dependent. Okay. Lattice dependent. So the property of the lattice is related to the energy of electron. So you can have some intuition that they are correlated. Then if we solve this equation, we see that this is cosine function. Cosine function cannot be larger than 1, right? And this one, sine and cosine, and we have a certain value here. And this one, if you go to the point where Ka is almost 0, then we know that cosine function is 1 in this approximation. Cosine function is 1, and sine function is almost Ka, and Ka is extremely small, and Ka subtract with each other, so this becomes P plus 1 at 0 point. So right hand side becomes P plus 1. Okay, so actually P is positive number. Okay, P is positive. So what does it mean? P plus 1 is larger than 1. So right hand side start from a value larger than 1. And there's a sine and cosine function. We know that when large Ka is phi, sine function goes 0, right? Cosine function becomes minus 1, right? Yeah. So it becomes minus 1 at the point of pi, right? Yeah, at the point of 2 pi, sine becomes 0, cosine becomes plus 1. So it goes here, goes to here. At the point of 3 pi, it goes minus 1. Just like we did for pi. And then for pi, sine 0, cosine plus 1. It goes here. Right? This is fixed point. So this function should pass through P plus 1 point, and then here, and here, and here, those dots, it should go through. So in that way you can draw the curve. I mean, near pi, for example, sine function actually pass through 0 value, and when it is between 0 and pi, sine function is positive, so it should be larger than this one. Right after pi, sine function goes negative, so it should be below here. So likewise, you can draw curves. Yeah, between pi and 2 pi, sine function is negative, so it will be negative here. Between 2 pi and 3 pi, it will be positive here. So it can be drawn like this. Okay? Yeah. Oh, this is another graphical method. And then left hand side, cosine KD. Cosine KD should be less than 1. Yeah, no larger than 1. So we know that this value, we take the absolute value, it should be larger than 1. Then it is allowed, we see there exists solution, and solution assigned large K value, right? Large K value will fix the energy. So we have certain energy value for the electron. Then we say that electron has the energy state. There are not only one state, there are many energy states. That's why it is banned. I will explain it again. And in the case of forbidden, okay, the value on the right hand side is larger than 1. then cosine KD cannot satisfy this equation anymore. So there is no solution. So there's no K value, so no energy value. So it is forbidden. There is no energy state existing. No energy state. And when you draw the curve, this one, and then you compare it with cosine KD, and cosine KD could be any value because K is the wave factor. Actually, K has M integer, L is the scale of the crystal. Crystal scale could be pretty large. Okay, it's macroscopy, we can say. So M is starting from 0, plus minus 1. There are many different values. So our cosine KD could be various values between minus 1 and plus 1. There are any values between minus 1 and plus 1. So within this range, cosine KD could be assigned anywhere. And right hand side is changing like this. There is overlap here, shaded range, right? Then we have energy state. So large K has certain value, within this range. Then we have energy. Within this range, then we have energy. Within this range, then we have energy. But here, we don't have energy state, okay? Because now large K, we cannot have any solution. So no energy state here, no energy state here. And they are actually spread, okay? Not just single value, but around certain range, we don't have any energy state at all. So actually, there is energy state here, no state here. There are not only one state, there are many states. That's why we call it band. Not just single state. There are many energy states, and we call it band. And there's gap. Okay, gap. Right? And there's a band. Okay, another band, another band. There's a gap again. So this is actually band gap, and this is band. Okay. So you can read through this. Yeah, we rotated previous figure by 90 degrees here, because large K is proportional to square root E. So this indicates the change of energy, and we explained that there are energy state here. No energy state. There are energy state. No energy state. There are energy state. So they are repeated. So the shaded region where energy is allowed forms bands. In other words, there are many energy levels in each band. The valence electrons in solid will fill those allowed energy. Valence electrons in solid, right? So those are electrons in the outermost orbit of atoms. Will fill those allowed energy bands from the lowest. So let's say we have these many bands, and electron will fill from the lowest energy state. Okay. When you consider crystals, you have something called Avogadro number. Okay, from chemistry classes. What does it mean? Yeah, within that cubic centimeter of volume, you have this many atoms, 6 by 10 to the 23. Then these are actually number of atoms. So let's presume that each atom emit or donate one electron from the valence orbit. Then this will be almost the same with number of mobile electrons. Okay. Roughly speaking. Okay, so this number of electrons will fill the energy state from the bottom. So, okay, there should be many energy states to fill this all. So we fill the energy state from the lowest. So you might feel like this amount of electrons into here, and then another this amount of electrons into here, and another this amount of electrons here, for example. And then you fully used all the electrons, and then there is a band gap. So next band, you are available energy state, but you didn't fill the electrons into that energy state yet. That is called as conduction band. And right below that conduction band, we call it valence band. So this is the meaning of the conduction band and valence band. And as I said before, there are many gaps between bands, but we only care the gap between conduction band and valence band. And this is the important material parameter, band gap. And we ignore other gaps, okay? And this one is important gap we have, and we call it band gap. So in this regard, we can consider classification of solids. And Pauli exclusion principle says that each particular quantum state can only be occupied by one fermion. Electron is a fermion. So as I said, there are many energy states, and each energy state should be occupied by one electron. Then how many electrons do we have? Let's say we have 6 by 10 to the 23 electrons, for example. Then you should have 6 by 10 to the 23 energy state to fill the electrons. We start filling the available energy state of a crystal from the lowest. As I said before, the last occupied band is completely filled. It is called as the valence band, and it can be compared with partially filled or empty band. It is called as conduction band. It could be partially filled or empty, both okay. Then it is conduction band. In the case of metal, conduction band is partially filled without any external voltage or laser excitation. Still it is already filled. Then it's metal. Electron can move freely over space because there are electrons in conduction band. Conduction already means the electron can move freely, so that we have conduction. Insulator, the conduction band is empty, and the electrons in the valence band cannot move over space. Okay. Actually, if you see these band structures for metal, insulator, and semiconductor, we see that these are valence bands these are conduction bands. In the case of metal, this is actually Fermi energy. Yeah, electron is half filled, and these electrons around Fermi energy can move freely. In the case of insulator, valence band is fully filled, conduction band is empty, and there's a band gap. And band gap is too large, for example, 4 electron volt or larger. So that electrons which are filling the valence band energy state cannot go into higher energy state in conduction band because the band gap is too high. If the band gap is not high, like in the case of silicon 1 electron volt or gallium arsenide 1.5, then it is easily excited. We mean electrons in the valence band will go into conduction band by, for example, external voltage. Okay. Usually external voltage we can easily have like 1.5 volt, okay, from the battery, yeah, for example. 1.5 volt is applied to electron, the electron should have 1.5 electron volt, right? So insulator and semiconductor actually have the same structure of band, but their difference is the scale of band gap, right? So their structure is just the same. So if you think of sapphire, for example, it is considered as insulator, okay? But still you can define the conduction band of sapphire, valence band of sapphire, but the band gap is very large, 9 electron volt. But still, if you apply very high external bias, for example, then electron can be excited into conduction band. Still, it is excited. It can be excited very, very hard. So we just rather consider sapphire as insulator. Okay. So we don't want to use too much of electric charge or electric bias to use insulator. We just want to use structures with smaller band gap so that we somehow save our electricity. Okay. Right, that's it for today. Next class, we will consider some other concepts related with these band structures. Okay, so that's it.